Galileo Galilei, the oldest of 6 children to Vincenzo Galilei and Giulia Amanti, was born in Pisa, Italy on February 15, 1564. Galileo's contributions sparked a scientific revolution in the pursuit for experimental explanation for many mechanisms of nature, thus igniting the first golden age of astronomy. Let's take a look at his journey. At 17 years of age, he became a student at the University of Pisa in hopes of attaining a degree in medicine, a choice more his father's than his own. 3 years later, out of mere curiosity, Galileo measured the period of a lamp swing, and upon discovering no discrepancies between the period of a larger and smaller swing, he formulated the law of the pendulum, in which a period is independent of the amplitude of the spring. From this derivation, pendulums have been used to devise mechanical clocks and metronomes. The following year, Galileo dropped out of university due to a lack of interest in his area of study. Galileo then went on to question one of Aristotle's laws, in that objects that carried more mass fell at a faster rate in comparison to lighter weight objects. In a well-known thought experiment, Galileo dropped several balls, ranging in size and weight, off the top of the Leaning Tower of Pisa. To his surprise, it took the same amount of time for each ball to reach the ground, clearly observing a flaw to Aristotle's theory. Under the influence of gravity alone, Galileo concluded that all objects fall with equal acceleration. In other words, size, mass, density, or horizontal velocity have no effect on time. In 1592, he was then hired as a professor at the University of Padua, and Galileo then went on to teach geometry, mechanics, and astronomy. Under harsh economic times, Galileo invented a thermoscope to allow for the measurement of temperature variations. His invention outlined how the density of a liquid changes in direct proportion to temperature variations, leading to the development of the Galilean thermometer. In this device, small glass bulbs are filled with different colored liquids, sealed, and then submerged in a clear liquid. The weight of each bulb is fixed at a set value by the addition of a metal tag of varying weight beneath the bulb. Any deviation in density of the liquid within the bulb has no effect on results of the experiment, as the content is enclosed within a sealed container. The liquid, however, is an organic compound like ethanol, which changes in density in response to surrounding temperature fluctuations. At temperature conditions in which the bulb is lower in density to the surrounding liquid, it rises, and where the bulb is heavier than the liquid, it sinks. Soon after, he devised a military compass, an instrument composed of 2 rulers of equal length joined at the hinge. Various scales within the ruler allowed for complex mathematical calculations used by the military for aiming cannonballs and in surveying and navigation. Galileo had 3 children with his mistress Marina Gamba. Both daughters were put in convents where they were named Sister Maria Celeste and Sister Arcangela, and his son Vincenzo lived with Galileo after Marina married. Upon hearing news of the creation of a telescope by a Dutch eyeglass maker, Hans Lippershey, Galileo built a model of 20 times magnification. Galileo's greatest contributions arose as he focused this telescope into the night sky. Galileo turned his telescope towards Jupiter and saw what he believed to be 3 stars fixed in a line near the planet. When conducting follow-up observations the next night, he saw all 3 stars to the west of Jupiter. At that time, Jupiter was in opposition to Earth, so Galileo expected Jupiter to leave the stars as it moved from east to west, but found his hypothesis to be wrong. The stars seemed to be carried along with the planet, changing their position with respect to each other and to Jupiter, and that there were 4 of these objects. He concluded that these figures were actually the moons of Jupiter rather than fixed stars. So what did this mean to the world of cosmology? Well, at the time, it was ubiquitously known that Earth was at the center of the universe, upon which all other heavenly bodies revolved around. Galileo's discovery, however, questioned this argument, as there was now another center of motion, Jupiter. If Jupiter and Earth both had revolving moons, then what limits Mercury, Venus, Mars, or Saturn from also being a center of motion? Projecting his telescope now towards the sun, Galileo noticed darker patches of irregular shape moving across its surface, indicating that the sun itself was spinning. What Galileo unraveled from the motion and appearance of these sunspots was that the sun was changeable and that it rotated.
However, because the sun is figuratively just a big ball of gas, it does not rotate like the Earth. It rotates differentially. This explains why Galileo observed regions near the poles rotating more slowly than the equator. So how do sunspots form in the first place? Well, normal magnetic fields are like tubes that carry magnetism in a smooth path from one magnetic pole to the other. However, with this twisting rotation, the magnetic field of the sun becomes distorted, preventing the smooth configuration and instead allowing magnetic field lines to burst through its surface. The magnetic fields of sunspots thus impede on convection and avert any plasma or heat energy from reaching the sunspot. Think of a sunspot like a cap on a shaken soda bottle. The cap holds back fizz of the soda, just like a sunspot, a region of intense magnetism, holds back much of the heat arising from the deeper core, thus creating a cooler and darker surface. Now if you can imagine the eruption following a twist on the cap on a bottle, a parallel effect occurs with a further twist in the sun's magnetic field, whereby solar flares result. Under Aristotelian beliefs, the sun was drawn out to be an unchanging, perfect flat disk. However, Galileo's observations of moving spots meant that there was a change in the heavens, a flaw in the predisposed laws of nature. Furthermore, the slower the motion of sunspots measured at the poles in relation to the equator helped indicate that the sun was rotating on an axis, and served as a precursor to understanding and accepting that Earth may rotate on an axis as well.
In 1610 and 1611, Galileo wrote letters and drawings to different astronomers, contemplating the phases of Venus. His discoveries about Venus were a multifaceted approach that has allowed us to now understand what we know in modern day about our solar system. Let's get into the nitty-gritty of the works with Venus of this great astronomer. Galileo observed Venus with a telescope. At the time, the geocentric model was the accepted model of the solar system, and it played the Earth in the center of the universe with the planets, the sun, and the moon orbiting around it. The two subpopular models were Plato's models and Ptolemy's model, both of which assumed Earth as the center of the universe, but differed in their placement of the sun relative to the Earth. The other model that the astronomers had played around with was the heliocentric model, in which the sun was placed in the center of the universe with all the planets, including Venus, orbiting around it. After turning his telescope to Venus, he found that Venus went through phases, just like our moon. But the nature of these phases could only be explained by Venus going around the sun, not the Earth. So let's break this argument down. We understand that in the Platonic view, the Earth is at the center of the universe and the sun revolves around it, while the planets move along circles whose centers also move around the Earth. If this was all true, all Galileo would be able to see when he observed Venus would be its corners being illuminated by the sun. Essentially, if the geocentric model was correct about Earth being the center of the universe, Galileo would have only observed crescent phases of Venus. But as the story goes, this is not what Galileo observed. In fact, his observations challenged the long-held Ptolemaic view, because what he actually saw was that Venus displayed not only the crescent phases, but also two quarter phases and gibbous phases. The quarter phases occurred when Venus was perpendicular to the sun, where only half of Venus was being illuminated. As it came closer to the Earth, the angle of illumination changed, allowing for only the crescent phases of Venus to be seen. Finally, when Venus was right in front of the Earth at a 0-degree angle, there was obviously no illumination, leaving it completely dark. As it continued its path away from the Earth, he saw that Venus was making a crescent cycle, making its way to the third quarter. Afterwards, when it had almost, but not quite, reached the opposite side of the sun, he observed the gibbous phases, in which he saw more than half of Venus being illuminated. Galileo's work gave support for the heliocentric system, and contradicted the Bible, and brought him to stand in opposition to the Catholic Church. Galileo then traveled to Rome to persuade the Catholic hierarchy to open up the cosmological debate and allow him to make his argument.
After the heat died down, Galileo striked again, and this time, as you can certainly imagine, things did not work out for Galileo. He was made to recant his beliefs in the Copernican system and was found guilty for teaching heliocentrism. He was sentenced to house arrest for the rest of his life. At the age of 77, Galileo died, taking with him pride and acknowledgement in his life's work. He has been called a mathematician, an astronomer, a physicist, and a philosopher, but his title in history is as the father of modern science. Stop! Now think!
One of the leading misconceptions among people is the idea that Galileo's brilliant telescope observations proved the motion of the Earth. Galileo's discoveries had not proved the Copernican cosmological system, but they had provided a psychological framework for thinking about the cosmos in new terms. People wondered, how could the Earth keep the motion in tow as it orbited around the Sun? And wouldn't people be thrown off into space from a spinning planet? Also, if Earth was really orbiting the Sun, shouldn't there be tiny effects in the position of stars as Earth changed its vantage point? All of these questions and more were answered, but only after Galileo's observations had gained credibility. Back in the 17th century, while Galileo had failed to prove the motion of the earth, he had made it intellectually respectable to believe in something that counterintuitive. There was never a aha moment, because by the time that modern astronomy rolled around, everyone who mattered had long since been persuaded in the belief of a moving earth by Newton's Principia of 1687, where his mathematical studies of gravitation showed people why they would not be spun into space by a moving earth. Also, recovery of Halley's comet in 1758 provided another popular confirmation of the Principia and its physics. But back to the caveat I mentioned earlier, the phenomenon of moving stars. This was later explained by the discovery of tiny annular stellar parallax that demonstrated that the reason that the positions of stars didn't change as the position of Earth changed was because the stars were too distant to notice any significant changes. Essentially, Galileo's then seemingly crazy ideas and observations paved the way for more discoveries and validations to occur.
Stop! Now think!